In this video, we're going to finish up Chapter 9 looking at Section 9.5, Limiting Reactant and Yield Calculations. So in many chemical reactions, we know one reactant is going to be in excess. So we're saying this is remembering we have our reactants on the left side of reaction, our products on the right-hand side. One of the two reactants is going to be limiting, one's going to be in excess. So in a non-chemical analogy, let's think about putting a bicycle together. If we have 8 wheels, 3 pedal assemblies, and 4 frames, we're only going to have as many bicycles as our least amount of reactant. In this case, we're going to have 3 bicycles because we have 3 pedals assemblies, and we'll have 1 frame and 2 wheels left over. So we're going to apply this concept to chemistry. These 4 steps are going to be important when you're looking at limiting reactant problems. So make sure you're using these as we're working towards them on the rest of this video, as well as in class and for homework. The first step is going to be calculate the amount of product formed from each reactant. So this is going to be like a mole to mole or mole to mass problem, but you'll need to do it twice, once for each reactant. The reactant that results with the least amount of product is going to be our limiting reactant, while the one that has the excess reactant is going to result in more amount of product. Think back to our bicycle analogy. So the amount of product is going to be determined from your calculation in step 1, and in the case sometimes you might be asked for the amount of excess reagent, so you'll have to determine the amount needed to consume the limiting reactant and subtract. So this might be doing a mole to mole problem with both of our reactants. So let's look at a chemical example. We've talked about our chemical reactions and what coefficients mean. If you start with 5 molecules of hydrogen and 3 molecules of chlorine, how much HCl could we make? We can see here that our ratios are 1 to 1 to 2. So because we need 1 molecule of hydrogen for each molecule of chlorine, our chlorine limits the reaction. With our 3 molecules of chlorine, we can make a total of 6 molecules, and again, this is because of our coefficients. We'll have 2 molecules of H2 remaining unused. So this is on a molecular basis. Let's talk about a molar basis. How many moles of HCl can be produced from 4 moles of hydrogen and 3.5 moles of chlorine? What is the limiting reactant? So the first thing we'll do is calculate the amount of moles, and this will be very straightforward looking at what's given. So 4 moles of hydrogen, our molar ratio from our coefficients, giving us 8 moles of HCl. Again, we'll do this again for both reactants here. So we'll do 3.5 moles of chlorine multiplied by the same molar ratio, looking at our coefficients since it's 1, 1, 2, giving us 7 moles. So in this case, we know less HCl is formed with our chlorine. We're going to run out of that first. So that is going to be our limiting reactant. This also means the maximum amount of HCl we can form is going to be 7 moles. Here's a checkpoint that you should work through. It's going to look the same as the last example, but here we're going to have some additional steps because we're starting in grams. Pause the video now. Okay, so we'll start by calculating the mass of barium sulfate from each of our 2 reactants. So in the case of 200 grams of barium nitrate, we're going to multiply by its molar mass. This will then give us moles of barium nitrate. We'll multiply by our molar ratio on the coefficients, and then we'll multiply again by the molar mass of barium sulfate to give us 178.6 grams of our desired product. Now we also need to do this again with sodium sulfate. So sodium sulfate, we'll start with 100 grams, multiplied by its molar mass, again by its molar ratio using the coefficients from the balanced equation, and again by its molar mass of barium sulfates again, seeing that we have 164 grams. So since less barium sulfate is formed with sodium sulfate, it is the limiting reactant. So the maximum amount of product we can form will be 164.4 grams. And again, looking at significant figures. We also need to think about reaction yields. So if you've had some poor experiences in lab, you know that not everything can go according to plan like desired. So there are times where we need to calculate exactly what's the best case scenario for a reaction, or the theoretical yield, the maximum possible amount, versus your actual yield. So what did you get? And our percent yield is very simply going to be actual yield over theoretical yield. Thinking about a score on an exam, right? Actual is going to be what you got on the exam. Theoretical would be out of 100, and so that's how we're getting our percentage. So here, let's calculate the percent yield of silver bromide if 375 grams of the compound are prepared from 200 grams of MgBr2. So in this case, we need to isolate what's given and then compare that to our theoretical yield. So we'll start with grams of magnesium bromide, go to moles, and then to grams. So 200 grams times our molar mass times our molar ratio times its molar mass of silver bromide, and we're going to get 408 grams. So you can see here this looks very similar to our mass-to-mass problems. The last step would be taking our actual yield, taking 375 given from the problem, dividing by 408, multiplying by 100, and so our percent yield for this reaction is 91.91%. So this looks very similar to our mass-to-mass. The only thing is we're adding one step at the end where we're subtracting or dividing what's given by the number calculated. So here's another checkpoint for you to work on. Please pause the video now. So our goal here is going to start with our grams of aluminum, which is given in the question. We'll go to moles, and then go to grams. So 125 grams, again given at the beginning of the question, multiplied by its molar mass of aluminum, multiplied by the molar ratio, multiplied by the molar mass of aluminum oxide, gives us 236.3 grams. We're then going to divide what's given, 100 divided by 236.3, times 100, 42.32%. That is our percent yield. That's the end of chapter 9.